order on before I said those. Um, First, Kyle, I have an apology to make. I saw weeks ago, I don't know how many weeks, maybe not that long ago, that there was an email from you about test one, and I just assumed you were turning it in, but at the time I didn't read the email. I just saw that you had it out there. I saw there was an attachment, so I just figured he's turning it in, but I wasn't connected to a printer then, so I didn't do anything. And then what happened? Yuck. I can't get Houston in because that box keeps getting in the way. So let me go this way. Okay. So Houston's here. Well, I can't get my pen to write now. Good. Okay. So then I got swamped with emails and never did get back to it until last night or sometime yesterday. And I guess it was in the afternoon yesterday, and finally got to it and was getting ready to grade it, and I realized you had said you couldn't read it. You had sent me the attachment of how it looked to you, and I apologize for that, because if I had just opened it then, I could have taken care of the situation then, but I just thought it was a completed test. So anyway, I did do a PDF of that test, and I put it out there. Now the first test I was able to put under the week, I think it was week 4, believe it was, whenever it was, and that's where I put it. But then when I went to put the PDF, they wouldn't let me put another test there. So I put it as a Blackboard message. So it's out there under Blackboard messages. And that's why I wanted to. Yeah. Uh-huh. Oh, I see. Okay, so you could get it on your computer. Okay, I'm sorry. Okay. Um, yeah, because I thought something had happened like that. When were you in Cal 2? Was that in the spring or was that in the summer? In the summer. And didn't you have some that you couldn't? Yeah, right. Oh, you were. Well, I guess that was a surprise. I never knew you were good. No, I didn't say that. Okay. All right. So, okay. Well, it's out there in PDF form if anyone needs it. Okay. And, uh, and maybe that's why I didn't change. The old gray cells, they ain't what they used to be. I couldn't remember, but I saw that email. I went, ugh. So I went and took care of it. So anyway, it's there. And also, by the way, for everybody else and you, it's the second test is out there as well. The chapters 9 and 10, 9, 1 and 2, 10, 2, 3, and 4. That test is out there too. So uh, be working on getting at least that first test in. This next chapter is going to take a while, so you have a little more breathing room than you had. We only had 5 sections between tests and the last 2. This one we have 6, because we're only going through 11.1 through 11.6, so you have a little more breathing time. All right, any other issues, concerns, problems, whatever? Okay. Nothing else to bring up, then let me minimize this. This is sort of a small crowd today. My first class was 100%, but yesterday was a pretty low attending day. I don't know why, but well, one class was really good. Maybe 2 were okay, but the other couple were a bit on the low side. Okay, well today, because last time we did finish all we were going to do in chapter 10. Now I don't remember if I said this because I know we ran out of time right at the end of class. Let's go back and look if you got your books. If you don't, just bear with me. We didn't do 10.1. You're certainly welcome to look at 10.1 for ideas, paper topic, that kind of thing. Hint, hint, be thinking about your paper, okay? Because that's also, this week, the end of this week will be midterm, okay? So we're halfway there, folks. So please don't forget about your research paper. All right, but 10.5, let's talk about area under a polar region. If you think your major is going to require something like that, by all means take a look at it. If you have any questions about it, by all means ask, okay? But frankly, can't ever recall having to do area using polar coordinates, though I know I've done it before, but I don't think there was a necessity for me to. I think it was just in a calculus text I did it. So I don't know that there's that many applications for it, but take a look at it, okay? That was 10.5. Then 10.6 is polar equations of conics and Kepler's laws, and maybe I did mention this last time. Johannes Kepler would be a really good paper topic because he's, if I'm remembering my history right, I think he's the one that went to Newton and said, look, I've come up with these equations that work for planetary orbits and things like this, but I don't know why they work. Can you give me a physical rationale for why these equations work? And sure enough, that's when Newton had to come up with his laws of motion to justify, and to rationalize Kepler's laws. And here comes somebody. Let me see if I can get the person in. Miguel, otherwise known as Jesus, is here. Okay. All right, we got half the class here anyway. That's good to see. Wish the other half were here too. So anyway, there are things there, and section 7.6 is polar equations of conics and Kepler's laws. So if you think you may need that, by all means go for that as well. And I do believe that's all of chapter 10. So I'm not saying the rest of it wasn't important, but just practical usage, I didn't see as much of it. But vectors in the geometry of space, you'll probably be going to be using this. I know some of you have already had your physics. Others of you may be still yet to take physics. You definitely are going to be dealing with vectors, or you have dealt with vectors so far in your life, and you probably will continue. Though you may not call them that and think of that, you'll still be using the concepts always. So that's what chapter 11 is. Section 11.1, if I can get the screen to advance here, is vectors in the plane. Now what do we mean by that? 2 dimensions. We're going to stay in 2 dimensions for now. A plane, not an airplane, but a 2-dimensional space. So in other words, X, Y, that's what we're dealing with. Then we'll move to 3 dimensions, and we'll do lots and lots of things from that point on. So let's talk about vectors in terms, oh, here comes James. Good to see. Let me get him in before it blacks him out. So we're more than halfway there now. Okay. Okay, James. Okay, no, your microphone's off. Okay. Okay, glad you're here. Okay, I was just introducing and saying we're starting chapter 11 today. Let me go back and say what I said earlier. In case any of you were having trouble opening the first test, the chapter 8 test, I believe it was. Yeah, chapter 8 test. I put the PDF version out there. Someone else is going to come in. I think it's Laurent, but I can't admit him that way. Let me get him this way. Okay. Laurent Shack is here. Okay. So he's here. So, okay. Someone talking to me, or that's just someone's microphone on? All right. Okay. So we've got Laurent here. Okay. So we got 6 out of 8. Hopefully the other 2 will be coming in. We're missing um, Jemanuel, and we're missing Esther. So hopefully we will get those. For those who just got here, let me go back and say this again. In case any of you are having trouble opening the first test, because I know the version of Word I have on this computer. This is a loaner from the college. It's a fairly new computer, and it had a really recent version of Word, and not all of their graphics can other Word versions open. So I put a PDF of that first test out there as well, the Chapter 8 test. And then just recently I put Chapter 9-10 test out there, and I think I put both versions of that, both the Word version and the PDF version. Okay, because in one of my other classes I had people who were not able to read that too, so I went on and did that. I thought I had already done it for the Chapter 8 test, and Shaq, well, Ron came back in again, so he's here twice. Okay, so and then I put out the one for Chapter 10 and 9 and 10, 9 1 and 2, 10 2 3 and 4. All right, is there a question? Okay. All right, so we're starting in Chapter 11 today, which is vectors in the geometry of space. 11.1 is vectors in the plane, meaning we're only dealing with two-dimensional vectors here, x, y vectors, two component vectors. And now it won't advance. Okay, here we go. All right, the objectives for this section: we'll write the component form of a vector. And frankly, folks, that's the way to go. Okay, component form of a vector tells you everything you need to know. It's concise, easy to write, easy to deal with, easy to operate with. It's the way to go. We'll perform vector operations. I think my phone's ringing. It's one of my instructors, so hold on a minute. I'll pause the integrity here. All right. We'll perform vector operations and interpret the results geometrically. Now there again, we'll be performing them in component forms, which is the easy form, interpreting them geometrically, which is a convoluted form. Okay, but we'll handle that. And we'll write a vector as a linear combination of the standard unit vectors, which hopefully you're already used to do. But if you're not, it's a pretty straightforward process. Okay, so now I have to click on the slide again before it will advance. All right, so let's start with the component form of a vector. This is the first subtopic in 11.1. Okay, now many quantities. Whoa, here comes somebody else, and I can't see who it is now. James. So evidently James got kicked out and is coming back in. Let me make sure I marked him right. Yeah, I only had Jemanuel and Esther missing, so we got James back, hopefully. All right. So many quantities in geometry, in physics, engineering, all sorts of things, such as area, believe it or not, volume, temperature, that's a rather strange one, mass, oh, okay, I'm sorry, misreading it. Area, volume, temperature, mass, time, they're characterized as single numbers, okay? Area, just how much space something is doing. Volume, well, it's area on a plane, volume in space, okay? Temperature, just a number. Of course, it could have different numbers depending on what scale you use, but it just is a single number. Mass, how much of you there is, how much of the object there is. Time, just a number, okay? You can give it units, of course, but it's just a one-dimensional quantity, okay? Those are called scalar quantities. Just because they're scalar doesn't mean they don't have units. They do have units, but they're just scalars. The real number associated with each is called a scalar. From now on, that's what we'll be calling it. Rather than real numbers, most of the time we'll use the word scalar. Now, there's a reason for that. We'll get to it later. The other quantities, though, such as forces. Forces have a magnitude, but they always are associated with the direction. Force this way, a force that way, resulting force. Those are vectors. Velocity, vector quantity. Acceleration, vector quantity. Okay? They involve both magnitude and direction. In physics, you'll hit momentum, vector quantity. Okay? Now, some of the ones in physics they didn't mention here: energy, scalar quantity. Okay? Let me think of any others. That's enough, I guess. Oh, I was going to say this. Now, quite often we talk about speed. In everyday usage, speed and velocity, we use them interchangeably like they're the same. In physics and in science, speed is a scalar quantity, just how fast are you going, whereas velocity is a vector quantity. Speed scalar, velocity vector, SSVV. Pretty easy to remember that way. Okay? Actually, distance is a scalar quantity. Okay? How far something is away. But displacement is how you went to get there. That's a scalar quantity. I mean a vector quantity. So distance would be a scalar quantity. Displacement would be a vector quantity. Now acceleration just about always really is a vector quantity. However, we often talk about it meaning the magnitude of the acceleration without really worrying with the vector nature of it. But that is usually a vector quantity. But those quantities, force, velocity, acceleration, displacement, momentum, all those, they both have a magnitude just like these scalar quantities do, but they also are associated with a direction. They cannot be characterized completely by a single real number. Can't do it. Okay? You can talk about the magnitude of it. Yeah, that's a number. But the whole quantity, no, you have to know more than just the magnitude. Okay? And it won't advance again. Sorry about this, being really stubborn today. So here's what we use to represent a vector. A directed line segment is used to represent a vector. Now what do we mean by that? Directed means it has a direction associated with it. This directed line segment is different from that one, even though they may be exactly the same length, they have the same magnitude, but they're heading in different directions. Okay? So here is a representation of that. Line segment means it has a initial point and a terminal point. Okay? Quite often in trig, when you start talking about vectors, they say a directed ray, which has no limit on this end. Okay? Well, then you're talking about angles. So yeah, you really don't care where the end point is. Triangles you would care, but an angle itself is rays. This is a directed line segment, an initial point and a terminal point. And here's one way to refer to them. The initial point we give capital letter P to represent that, and we could, and we will, represent P, and now we're in the plane, folks, just in the plane, just two coordinate issues here. We could refer, if I could get my pen, there it is, we could refer to P as, say, x1, y1. Those are the coordinates of that point P. Coordinates. Point Q up here is obvious a different point. Okay? So it has different coordinates. Its x component coordinate is different. This x is over here. This x is over here. Obviously different. Its y coordinate is different. This y coordinate's down here. This one's up here. So that's be this. So those are coordinates of a point. Now I'm bringing this up later. Now for later. One way to represent that vector is to write it as PQ. And notice we put a little vector symbol over it. That's a little directed line segment over it. Okay? Now, always we list the initial point first, the terminal point second. Just like the arrow is pointing toward the terminal point here, the arrow is over the terminal point here. So that's how we do it. PQ and QP would be different vectors, same magnitude but going in opposite directions, like that. So you'd have to know which is first, which is your initial point, which is your terminal point. Okay, terminal means ending. Initial point means beginning, terminal point means ending. A directed line segment. The directed line segment PQ has initial point P, terminal point Q. Its length, also called its magnitude, okay, is denoted by double brackets here, PQ. Now those two, they're not brackets, two straight lines, they look a lot like absolute value bars. And that's not a bad thing to associate them with, because just like an absolute value is never negative, the magnitude or the length of a vector is never ever negative. It could be zero, those are really not very interesting vectors, but it's never negative. So no matter which way it's pointing, its magnitude is always finite and positive. Okay? Now, what if you had a whole bunch of directed line segments that have exactly the same length or magnitude and are pointed in exactly the same directions? Okay? These are called, they're not the same vectors, but they're called equivalent vectors. And one of the concepts that you have with vectors, vector has a length and a magnitude and a direction, but it doesn't matter where in space it's located, the vector has a magnitude and direction. It's a directed line segment, has a length, has a direction. That's what makes it that vector. So all these are actually equivalent to one another. Well, I can't do it. Equivalent to one another because they have exactly the same length, exactly pointing in the same direction. Those are all equivalent directed line segments or equivalent vectors. Now, the set of all directed line segments that are equivalent to a given directed line segment, say PQ, if that was our first one, that then is a vector in the plane, and that vector, okay, in the text, they represent vectors as bold, lowercase letters. And their favorite of all times is V. But they also have U. They could have anything, but their favorite is V. But U, V, and W are the ones they use the most, with V being the most common. Okay? So that vector V represents any vector that's of the same magnitude and the same direction as PQ. So PQ is one particular because it has one initial point, one terminal point. V would represent any vector that has that same magnitude, same direction. Okay. So in typeset material, vectors are usually denoted by lowercase, bold-faced letters such as U, V, and W. They're the ones I mentioned before. I can't write boldface. So what I write is this, V with the arrow over it. Just like you put it over PQ, that lets you know I'm talking about the vector V rather than a variable V. Okay, that indicates it's a vector, meaning it has both magnitude and direction. When written by hand, that's what it says here. However, vectors are often denoted with arrows over them, like U, V, and W would represent these same three vectors here. Now these are italicized. I don't write italics either. Okay, they're just like that, V with an arrow over it. Okay. Now if it's just a bar over it, that usually means average value. So don't confuse that. You have to have a little arrow point on it. Okay. Be sure you understand that a vector represents a set of directed line segments, each having the same length and same direction. So that vector V could be any place in the plane. Later we'll do it any place in space, but any place as long as it has the same magnitude and same direction. In practice, however, it's common not to distinguish between a vector and one of its representatives. We just call it vector V. And we usually think of that as just one vector. and other times we'll refer to a vector and give it PQ, but think of it as any vector parallel to that and same length. Okay. So here's example 1. Let V be represented by the directed line segment from 0, 0, good place to start, to 3, 2. Now let U be represented by the directed line segment from 1, 2 to 4, 4. Show that V and U are equivalent vectors. In fact, when you write them like this, they would be literally the same vector, because this represents a set of all vectors of that length and direction, and this represents the set of all vectors, U represents that. So you'll find out they are equal. Okay, so how do we know whether they're equivalent or not? Well, number one, they have to have the same length. What's the magnitude? Distance between 2 points, square root of x1, x2, 3, minus x1, 0, squared, plus this y2, 2, minus y1, 0, squared. So this would be the square root of 9 plus 4. That would be the square root of 13. Now, that's its magnitude. Also written this way. Okay, let's do the one for U. The magnitudes for U would be the square root of 4 minus 1 squared plus 4 minus 2 squared. Y2 minus x2 minus x1 squared. Okay, that would be the square root of 3 squared plus 2 squared. Hey, that's exactly the same thing. This is the square root of 13. Okay, does that mean they're the same equivalent vectors? Not necessarily. That's just the first step. The second step has to be, are they going in the same direction? Now, without getting too involved here, let's just remind ourselves that one way we could represent direction, and that would be slope. And slope is change of y over change of x. So if they are the same magnitude or length and have the same directions or slope, then that would work. Well, change of y here was 2 minus 0 for this one, over 3 minus 0 for that one, 2/3. Over here, your slope for U here is 4 minus 2 over 4 minus 1, which is equal to 2/3. Yes, the slopes are the same, meaning direction, and the magnitudes are the same, meaning length. So yes, those are equivalent vectors. You need both. Just showing they have the same magnitude doesn't guarantee they're the same vectors. Just showing they have the same slope doesn't indicate they're the same vectors. They have to have both the same magnitude and the same slope. Make sense? Now let me erase my scratch here, if I can get to my scratch. Okay. So here's your P 0, 0 to 3, 2. There's your PQ. There's vector V. And then when you draw it, they sure look awfully close, but looking isn't good enough. You have to validate that mathematically. And here's the one from 1, 2 to 4, 4. They sure look about the same length. They sure look to have the same direction, but you verify that by calculating the direction. You can use the distance formula to show they have the same length, square root of 13, square root of 13, and then you can use the slope formula to, now this, get this, this works in 2 dimensions. Sort of hard to talk about slope. That same formula won't work in 3 dimensions or higher. Okay, so in 2 dimensions you can use that. The slope of this one's 2/3 and the slope of that one is 2/3. So sure enough, they are equivalent vectors. In fact, you could say the same vectors. They have the same length, same direction. You can conclude they are equivalent. That is, we actually usually write this, believe it or not, and they say equivalent. Somewhere here is my pen. There it is. Okay. Well, there it is. We would say V is equal to U. We say equal to because they are the same vectors. Remember, they represent any vector with that magnitude and slope, so they are the same. Okay. Now, the directed line segment whose initial point is the origin, like P was, okay, is often the most convenient of the line segments to use to represent that. Other times it may be good to use some other representation, but most of the time that's the most convenient. Okay, it's shown there. All you've done is translate it from here to here, but it's just so much easier to write here, and we'll see why in just a moment. Okay, that representation of V is said to be in standard position. Now again, what does that mean? Initial point, the origin, terminal point, wherever it turns out to be. A directed line segment whose initial point is the origin can be uniquely represented by the coordinates of that terminal point. And the reason is because V1 minus 0 is V1 and V2 minus 0 is V2. Now notice the difference here. When you're talking about points, coordinates of a point are written with parentheses around them. Vectors, however, the components of a vector. The words are similar but different. Components of a vector are inside angle brackets, V1, V2. When the initial point is 0, these two representations are just about identical. The only difference, these are parentheses, these are angle brackets is what I call it. I've never heard a name for it. I don't know what that means. If I'm getting an email, I don't know what it means, but I've heard it. Excuse me. Sorry about that. Even though I moved the mic, it probably still blew your ears out, right? Sorry about that. I don't know where that came from, but it came from somewhere way deep. Okay. So just get used to this representation. This is called component form of a vector. When that vector has its initial point of the origin, the coordinates of the terminal point are exactly the same as the components of the vector. Okay, that's when it's a standard position, and that's what we like to use as component forms. Whether the initial point is here or not, you still like to use the vector in component form. In the definition, note that the difference in notation between component form of a vector, V with angle bracket, V1, V2, and the point, whoa, they mess that one up. If it's a point, that should be parentheses. Did they mess that up in the book too? No, in the book they got it right. On the slide set, they don't. That should be, I've never noticed this before. I'm sure I've taught this chapter before. That should be parentheses here. In the book it's correct. Here it's not. The point is in parentheses. Vectors are in angle brackets. Now what I was going to say before, I call it angle bracket. I don't know the actual name of it. A bracket is actually, if I can find this, a bracket is that. Okay? This is a parentheses here. This is a bracket. This is a brace, just to get your terminology. I don't know what they call those things. I've never read what they call them, so I call them angle brackets. Okay? May not be what they're called, what they are officially called, but that's the name I came up with and I'm using. Okay? Now, so here's a definition of the component form of a vector in the plane. In the plane meaning two-dimensional vector. If V is a vector in the plane whose initial point is the origin and whose terminal point is the point, terminal point is, this is a point, so it's in parentheses, V1, V2. See, that should be the same as this, okay? V1, V2, then the component form of the vector is also V1, V2, but inside angle brackets indicating it's a vector, not a scalar. The coordinates of V1 and V2 are called the components. The coordinates of a point are called the components of the vector. If both the initial point and the terminal point lie at the origin, then you have what they call the zero vector. Now, here's my problem with the zero vector. You have to have it, absolutely necessary, but here's the problem with it. It has no magnitude, it has no direction, okay? So therefore it doesn't seem to fit the bill for what we mean by vector. But yet you have to have it there for other purposes, which we won't get into now, but you have to have defined the zero vector, and that's a vector whose initial point and terminal point are both the origin. Or, if it's somewhere other than the origin, they're both the same. 3, 2, 3, 2. Okay, that would be the zero vector. Okay, now we designate this, every other vector, oh goodness gracious, look at that. Every other vector is given a boldface lowercase letter. The zero vector is given a bold 0. This is the only time you'll see a number used to represent a vector. You can do components of vectors or numbers, but to be the boldface, or I can't write boldface, so I put 0 with an arrow over the top. I didn't draw a very good arrow there. That's the zero vector, and it's designated by components 0, 0. No magnitude, no direction, and yet it's still called a vector. Okay, the only one that has no components and no direction. That definition, I'm sorry, I'm having trouble with my voice. Hold on. I did eat lunch too quickly and probably didn't drink enough water, so that may be part of the reason my voice is coming and going. Okay. That definition implies that two vectors, u, u1, u2, and v, v1, v2, are equal. Now we're not saying equivalent anymore, but equal if and only if u1 is equal to u2 and v1 is equal to v2. Now remember, those aren't coordinates, those are components. So what we were calling equivalent vectors, we're now calling that they are equal. Okay? Wow. Okay. So, let's move on from there. The procedures listed below can be used to convert a directed line segments to component forms or vice versa. So let's say we have P, which is not necessarily at the origin. It has point, the x coordinate is P1, the y coordinate is P2. And we have some other point Q, different from P, such that its components are Q1 and Q2. Notice the parentheses indicating these are components, I'm sorry, I'm saying it wrong, coordinates of a point. Parentheses means coordinates of a point, P, coordinates of the point Q. These are the initial and terminal points of a directed line segment. Then the component form of the vector V for any old generic P1, P2 here, Q1, Q2 here, it would be this. The first component here would be the difference here. Always terminal minus initial. Always terminal minus initial. And you do that for the first component, coordinate. You do it for the second coordinate or component. So it's Q1 minus P1, comma, Q2 minus P2 in angle brackets. That's your components of the vector V, represented by that vector PQ, where P is initial, Q is terminal. Always do terminal minus initial for each component, each coordinate. Moreover, from the distance formula, you can see that the magnitude, which I've already talked about, of the vector is the square root of, now, here it doesn't matter the order. They write it as if you still do it that way. It really doesn't matter. But because up here it does matter big time, it's good to get into practice doing Q1 minus P1 squared plus Q2 minus P2 squared. Okay? See, the reason the order doesn't matter, reverse those two, they're negative of each other, square it, you get the same answer. Okay? Same thing here. Reverse those two, you get the negative of what you had before, square it, you get the very same thing you had before. Now, notice this is the principal square root, the positive square root. That's why the magnitude of V is always, always, always positive, except for one exception. The zero vector has no magnitude, has a zero magnitude. So the other way to write this then, since this is, especially if you write the Q1 minus P1, this is component V1 squared, and that's plus component V2 squared. That gives you the magnitude of a vector. So if you're given initial and terminal points, calculate it that way. If you're given component form, initial and terminal coordinates of the points, do it by subtraction. If you're given the component form of a vector, square the first, square the second, add them together, take a square root. Okay, that's the length of a vector or the magnitude of a vector. Now, time out just a moment here. I've got 3 people here today who are currently in linear algebra. Okay, your linear algebra text is written by precisely the same author as this one. Now, this one is Larson and Edwards, but Larson is the main author. Okay, in your linear algebra text written by the same guy, he doesn't use angle brackets there, he uses parentheses. And in that case, you have to determine whether you're talking about components of a vector or coordinates of a point strictly by the context, which is different. If he says a point P, you know they're talking about coordinates of a point. If he says vector V, you know he's talking about the components of a vector. But he uses that same notation, and I do not know why. If you recall, he was the author of your pre-calculus algebra and trig book. He also used angle brackets there, especially in the trig portion. Okay, I think Sir Manuel came in. Good deal. Let me get him here. And now we're only missing Esther. So it turned out being a good attending class again. You usually are. So Jemanuel is here. We're only missing Esther. Does anyone know if Esther has ever gotten her PowerPoint, her Blackboard to respond? The last I heard, she was not able to get into Blackboard, and that's why she couldn't come to class. Okay, Emmanuel's coming back again. And he's coming back again. And he's coming back again. I don't know why it's taking him so many times to come in, but let's admit him again. All right. And there he goes again. So he's coming and going. Evidently he keeps getting bounced out, and I'm bouncing him right back in. Y'all can't see this, but it's happening. Just time after time. So he's in the waiting room again. I hit admit. It shows him admitted, and then it shows him back out again. And I don't know why. If any of you can get in touch with him, tell him I'm admitting him time after time after time, but he keeps getting bounced back out again. Or he's bouncing himself out. I don't know which. I couldn't imagine he'd be doing this to himself. Okay. Are any of you able to get in touch with him? He's just doing it over and over and over again. What's that? You think his Wi-Fi's? That's what it sounds like. Okay. So he's out again, and he's out again. I admit him back. He's here. Now he's out. Admit him back. He's here. Now he's out. I admit him back. I don't know. I mean, I hate to take class time doing this, but I want him in the class, but I can't make him stay. Here he goes again. If you do watch this on YouTube video, you'll see how many times I've done this. Over and over. I mean, he's out, he's in for a fraction of a second, or maybe a second or two, and then he's out again. Has anyone gotten in touch with him yet? Well, that time it looked like he stayed a little longer. Thought he was in that time, but bumped right back out again. This time it's taking him longer to join. Maybe this time it'll stick. It's taking him longer. It's still joining. So he's in the waiting room, but he's trying to get in. Nope. He got in, and then it bounced him right back out again. All right. Do any of you have any suggestions? Hey, this time it seems like he is in here longer. Okay. All right. Except I don't think he tried to get back in that time. He's not in here. So evidently he gave up trying. Uh, if you can get in touch with him, tell him I admitted him every time he popped up there, but I don't know how many times it was. I think probably more than 20, but I don't know for sure. Up! I think he's coming again. They blacked out his name. So let me try him again. This is one other reason I tend to agree with. All right, this time I think he's in. Jemanuel, are you here to stay this time? All right. Goodness gracious. I kept letting you in and you kept popping right back out again. Was it your Wi-Fi or something else? Really? Well, the others can attest. I kept saying it. If you watch the YouTube video, you'll see how many times I let you in and then you'd pop right back out again. See, Laurent didn't want you in and he kept knocking. No, I'm just kidding. Okay. All right. All right. Okay. So let's get out of that. We got everyone here but Esther. I hope that Esther can finally get her Blackboard. This Blackboard Ultra is not my favorite. Uh, it may be, folks, just to give you a heads up. Of course, most of you are probably moving on soon, but it may be in the future they're going to go to a different course management system than Blackboard. So guess what? That'll be something else new to learn. But for those who, I think every one of you are planning to transfer, I don't know that many four-year schools that do use Blackboard. A lot of them use one of these other packages like Canvas or Moodle, or there's one called DS2. So actually you'll be wishing that we had changed earlier, probably, because you're going to have to learn it anyway. All right, so Jemanuel, we are in chapter 11. That's vectors in the geometry of space. 11.1 is vectors in the plane, meaning just two-dimensional vectors. We've been learning about them. We just finished this slide we're on now. This is slide number 15, and this is basically the verbiage that is on page 753, right near the middle of the page. Okay? Two ways to talk about the magnitude of a vector. It's either the difference of the first component squared of the 2 points plus the difference of the second component squared, take a square root of that sum, or if you have it in component form of a vector, the component of the first component squared plus the second component squared, take a square root of that. Principal square root meaning always positive. The only time it's not positive is when you have a zero vector. That means you have no magnitude and no direction. You're at the same point. Okay, so let's see if I can click on the slide and move on. So that was point one. That's one procedure. Here's another. If the vector is given as v1, v2, these are components forms of the vector, then v can be represented by the directed line segment in standard position from initial point 0, 0, terminal point, the same coordinates for your terminal point as your components of your vector if the initial point is 0, 0. Now, the length of a vector v, we've already called it the magnitude of v. The other name for it is the norm of v. Okay? Length, magnitude, norm. Now, if that norm or length or magnitude is equal to 1, then we say that v is a unit vector, meaning it has magnitude 1. Moreover, if the magnitude is 0, that's true if and only if that vector v is the zero vector. That's the one and only vector we use a boldface number to represent, and that number is 0. That's the zero vector. Okay. Most vectors are going to have magnitudes or norms or lengths other than 0 and 1. So most vectors are going to be all over the place. It's going to be very short vectors, very long vectors. Okay. Large vectors greater than 1, small vectors between 0 and 1, but the two special ones are if the magnitude is 0, it is the zero vector. If the magnitude is 1, it's called a unit vector. Now you can have a unit vector in all sorts of different directions. If its magnitude is 1, it's a unit vector. The zero vector has absolutely no direction, no magnitude, so it doesn't make any sense talking about that. All right, now I think they're skipping example 2. So let's go back a slide and let's do example 2. I make a rhyme every time. Okay, so we'll go to the whiteboard. Since it's our first trip to the whiteboard, it means I've got some maneuvering to do, which you probably can't tell. In my whiteboard, there's a taskbar that sits taking up white space. I don't want it to happen. And then because I've got you guys, or at least 4 of you, and me lined up over here on the left, I have to move my whiteboard lined up to the right. I have to move my whiteboard as far as I can to the left, and also up as far as I can to get maximum white space to work with. Okay, so here's example 2. I'm going to have to get the book in my lap because, okay, they have buttons on this pad. I don't know why. I haven't ever figured out what good they are, except to give me problems. Find the component form and the length of a vector v. So here's our vector, if I can get my pen in the right direction. A vector v, since I can't write bold, I'll put the arrow over it, that has initial point 3, -7. Definitely not in standard position. You can tell that. That's a point, so it has parentheses. And terminal point -2, 5. Okay? The question is, give this in component form. So what would be the component form? Component form of a vector would be angle bracket on either end, comma in between. We need a number here and a number there. What would be the leftmost number? Vector V would be the vector from, always terminal first, -2 minus the initial first component, coordinate. That would be a -3. Minus because this is subtraction here, 3 because that number. This is a negative sign, so that goes with the 2. Comma, 5, the terminal coordinate, minus a -7. Okay, so this would be in component form. What does that add to? This is 5 minus a -7, which is a +7. 5 plus 7 is 12. So there's the first part of our answer. Here is this vector here written in component form. The second part of the question said, find the length of the vector. Now, the length of the vector is also called the magnitude of the vector, and it's also called the norm of the vector. Okay, and what that is the square root of its component squared, the sum of the component squared. -5 squared plus 12 squared, which is equal to the square root of 25. It doesn't matter whether it's positive or negative, you square it, it's going to be positive, plus 144, and that would be the magnitude or the square root of 169. And if anyone happens to know that, that is 13 on the nose. Positive always, unless it's 0. And this is not 0, so it's going to be positive. 13 is the magnitude of that vector. Component form, -5, 12. Magnitude, what did they ask for? They actually called it length. Norm is 13. Yuck! This book is heavy. All right, flipping over to page 754. Okay, that leads us into where we were on the PowerPoint, which is vector operations. All right, we start with some definitions. First, vector addition. And you'll see vector subtraction is very, very similar. Okay, let U, represented by U1, U2, components, okay, and V, represented by V1, V2, they're in angle brackets, they're both vectors. C is that scalar. Okay, now remember, scalar means any real number. It could be positive, it could be negative, it could be fraction, it could be a decimal, it could be a rational number, it could be an irrational number. Any real number, C. Okay, now what do we mean by the vector sum of U and V? That means you add vector U to vector V. That's what a sum means. Well, how do you do that? You add like components, U1 plus V1, comma, U2 plus V2. It's that simple. You just add the corresponding components together. It's still a vector, so you put it in vector brackets. Okay? Now, the scalar multiple. Remember, C, any real number, positive, negative, fraction, decimal, rational, irrational, it doesn't matter. The scalar multiple of C with that one of those vectors, U, is then C times U. And actually, You could have done it like this, and I think this would have made a lot more sense if they had done it, but it's perfectly right the way they did it. If I could find my pen. There it is. Okay. If they had written in between these two, said C times U1 comma V1. Now it looks like you're distributing in. That's exactly what you do. You distribute the C in to both terms. So CU1 comma CU2, still a vector. Scalar multiple of a vector is a vector. Time out a moment. I said that I would tell you why they use the term scalar, especially when you're talking with vectors. What if C is a little number? Okay, and U was some vector like this. Multiply it by C, you've now scaled that vector down. You keep the same direction, but you scale its length downward. But what if C was a big number, like greater than 1? Then you're scaling it upward. Same direction, you've just scaled it differently. So that's why they call it a scalar. Okay? Any real number. Okay. The negative of a vector V is the vector negative V. Okay? And here they did show, if I was on the right pad, just factor out or write that negative as a negative 1 times V, then distribute that across the vector V. They were using U, now V. The negative distributes across the inside, so it's negative V1 comma negative V2. You negate both components. Remember, one of those components, or both of them, could have been negative to begin with. You negate them, and they would have either one or both become positive then. Okay. Now, I told you vector subtraction wasn't much different, and here's what it is. The difference of vector U and V, that would be U minus V, would be the same, just like we do it in sign numbers. You add the opposite, okay, or add the negative. So U minus V would be U plus the negative of V, or the opposite of V. And then that would be U1 minus V1, comma, U2 minus V2. So you subtract the components, just like adding two vectors, you add the components, subtracting two vectors, you subtract the components, always the one in front minus the one second. Do that with the components as well. In adding, it really doesn't matter because U1 plus V1 is the same as V1 plus U1. But remember, in subtraction, U1 minus V1 is not the same as V1 minus U1. In fact, they're exactly opposite of each other. So in the difference of two vectors, you have to keep up with those minus signs. They're only there to trip you up and make you mess up. Plus signs, you can do anything you want to with. So there are the vector operations. Geometrically, now this is where I don't see a lot of advantage of this except sort of what I've already said. Geometrically, the scalar multiple of a vector V and the scalar C is the vector that is the magnitude of C times as long as the vector V. So if that C was 1/2, then that's 1/2 as long as V. Here's vector V. If it's 1/2 of V, it would now be exactly the same direction, but half the length. If it was twice V, it's exactly 2 times the length of V, but in exactly the same direction. If that had been a minus V, we now represent it as we just flip it around. The initial component of V becomes the terminal component of minus V. The terminal component of V becomes the initial component of minus V. And then we could also scale that up or down too by increasing the magnitude if it's greater than 1 or decreasing it if the C is less than 1. Okay. Now, if C is positive, then CV has the same direction as V, but if C is negative, then it's always in the opposite direction. You reverse the direction. My throat is going on me awfully fast. I hate to feel this. I don't know if it's change of weather or what the problem may be, but I'm losing it. I don't know if that helps, but it sure makes it feel better. Okay? May not do anything but a placebo effect. I don't know. All right. Now, any questions on vector operations? Now, how do we represent the sum of two vectors? Now, this geometrical representation, I guess, is beneficial, and in physics, usually pictures are helpful, so yeah, it's not a bad idea. The sum of two vectors can be represented geometrically by positioning the vectors without changing their magnitudes or direction. Remember, then they'd be different vectors, so that the initial point of one coincides with the terminal point of the other. Okay, so here you have vector u going up here, vector v going down here. Okay, if you're talking about finding the sum of u and v, remember this vector v is the same wherever it is in the plane, as long as you don't change its magnitude and don't change its direction. So translate this v up here so its initial point is sitting on top of the terminal point of u, and then let the terminal point of v point however it is, because you don't change its magnitude or direction, and what you've done is moved it from here up to here. Okay, the resultant vector, the sum of those two vectors, would be this vector here. Now, notice this. The magnitude of u plus the magnitude of v is just about always greater than the magnitude of u plus v because of that angle in there. The only time they're not is if u and v are collinear in exactly the same direction, then the magnitude of u plus the magnitude of v may be the magnitude of u plus v. But that's the only time. The rest of the time, u plus v will have a magnitude less than the sum of u, magnitude of u, and magnitude of v. Okay? Just a little point there. Now, what though if you had taken v first and then translated u down, so its initial point is at the terminal point of v, and its terminal point is wherever that would put it? Guess what? When you translate u down here to the terminal point of v, you get exactly the same vector u plus v. Now, not located the same place on the plane, but same magnitude, same direction as you had up there. So for adding two vectors, that's a commutative process. It doesn't matter the order in which you add them. Subtraction, it matters big time, okay, but addition, it doesn't matter. Okay? Now, the vector u plus v is sometimes called the resultant vector, also called the sum vector, okay, whatever. It's the diagonal of a parallelogram. Now, here's another way they do it, and this is fine too, just seems like extra work. If you really put these on top of each other, okay, v and u on the lower side here, u and v on the upper side here, and bring that same, bring them somewhere in the middle, either of these two places, bring them together, you form a parallelogram. This one represents, especially if you put it at the origin, okay, then this would be u plus v here, or this would be v plus u here. Now, the advantage of putting that initial point of whichever one you're dealing with, v or u, in other words, putting them both at the origin, and then moving the one that you're do this one here or this one there. The advantage of doing that, now you see why that component addition works. Vector u has a very short u1, relatively large u2 right here. Add to that v, which has a pretty long v1 and a pretty short v2. Well, if you add this v1 to that u1, you get this initial magnitude here, the magnitude of your initial point value, initial component, u1 plus v1. See, there's v1, there's u1 that you got from here, okay? And then the vertical component, if you started from here, you went up u2, but by starting from here, you had already assumed you were up v2, so that would be u2 plus v2. And sure enough, that's what your component, adding the components of a vector, does for you. So much easier than trying to do it geometrically, way easier. Now, scalar multiplication, if this is your vector u here, you're multiplying it by a large scalar, k greater than 1, then your first component is ku1, second component is ku2. Why they didn't put it over here, I don't know. This is u1 here, u1 here, u2 here. You scale this up by k, scale that up by k, you wind up being collinear with the original vector. Goodness gracious, my throat's going. And for 3 hours, you've got another class coming. So, all right. Now, the subtraction, I just as soon not do this, but they do it. I'll show it to you. I don't ever think of it in terms of the parallelogram. You could, but I just don't think it's worth it. I do think of it this way. If you have the vector u minus v, draw the vector u first, and then take the vector v, change the direction exactly opposite, and then translate this up here, and that gives you your resultant vector here, u minus plus a minus v. You see, you took the v, made it a minus v, and then you get u plus a negative v here. All right. They like to then do this, u minus v, this way, which certainly is true, but to me, it's not worth trying to memorize. Guess what the easiest way to do? Subtract the components, okay? These parallelograms, they're just, I don't want to say a waste of time, but they're unnecessary. Just add, subtract, multiply the components. That's all you have to do, okay? So let's go to example 3, okay? Here's vector v, negative 2, 5. Vector w is 3, 4. Let's find each of these. So first, the a part, 1/2 of v would be 1/2 of negative 2, 5. Just write vector v as that. And then distribute this inside. It is still a vector. 1/2 of negative 2 is negative 1, and 1/2 of 5 is 5/2. You could write it as 2.5 if you wanted to. It doesn't matter. There's the a part. The b part. Write it like it is. That's w, which is 3, 4, minus v, and v is negative 2, 5. And what is the resultant vector there? 3 minus a minus 2, that would be 3 plus a 2, which would be 5, comma, 4 minus a 5, which would be minus 1. Did y'all want to do a parallelogram? No, they're just not worth it. So much time is spent drawing it, doing, and then your lines aren't really good. Yeah, just do the math. Let the components do the work for you. Okay, how about this one? V, negative 2, 5, plus 2 times w, that would be 3, 4. Now here I want to say, use your rule of order of operations. Please excuse my dear multiplication before addition. So just leave your v alone, negative 2, 5, multiply first, scalar multiplication, plus 2 times 3 is 6, comma, 2 times 4 is 8. Now do your addition. Negative 2 plus 6 is 4. 5 plus 8 is 13. Boy, can it get any easier than that. So what we got, this is example 3, was negative 1 5/2. That's what the book had too, in angle brackets, by the way. The next one was 5 negative 1, perfect. And next was 4/13. Got it. So let's see how they did it, to see if they did it any differently from what I did. I can't imagine why they would choose to, but they could do it slightly differently. Let's see if there's another way. Nope, just multiply. Yeah, they wrote an extra step in there, which I found actually more trouble than it's worth, but it's okay. You know, you distribute the 1/2 inside here and the 1/2 there. It's exactly what we did. Why write it that way, I'm not sure, but they did, and that gave us negative 1 5/2, exactly like we got it. Okay, then the B part is W minus V, and they wrote the components out there, W1 minus V1, comma, W2 minus V2. Then they plugged them in, 3 minus a minus 2, comma, 4 minus a 5, and that would be 5, comma, minus 1. Got it. Exactly the same way, just approaching it a little differently. The C one, V plus 2W, would be 2, a negative 2 5 was your V, and then they said 2W is twice W, which W was 3 4, twice W would be 6 8. So add those two together. Why they wrote it that way, I don't know, but it still gives you the answer. Now they show you every step here. Negative 2 plus 6, comma, 5 plus 8, and that's 4/13. Any questions? Pretty straightforward. Don't draw parallelograms unless you have to, unless you're just trying to illustrate what's going on in a physics problem. Then they're helpful. You can see what you're trying to represent. When you're doing this, just use component form. If you got it, use it. All right. So here then follow some of the properties of vector addition. Okay. Now, I like to put a few more words in than they do. So we got U, V, and W are all vectors in the plane, meaning they have 2 components each. Okay. C and D are both scalars. That means any real number, positive, negative, fraction, decimal, rational, or irrational. Now, if you're adding U to V, like we said before, that's precisely the same as adding V to U. Why? Because the components are numbers, and numbers commute under addition. So if I were calling this, I'd say commutative property of addition. Okay, I would put that in there. In fact, I would say of vector addition. Okay, this one, if you add U and V together and then add the vector W to it, you get the same result if you had started with vector U and added to that V and W added together. That's the associative property of vector addition. Okay, I like to always put those words in as well. Sorry, man. I would say that's probably not doing any good, but it feels good. Okay, now if you add U to the 0 vector, guess what? You get U, because this would be U1 plus 0 is U1, U2 plus 0 is U2. That U1, U2, that's U. Okay, that's U. Okay, no. All right, that is the additive identity property of vector addition. The 0 vector is the additive identity element in vector addition. In other words, you add it to any vector, you get the same vector. Turning that around a little bit, U plus its opposite, the negative of u is always going to produce the 0 vector. That's called the additive inverse property of vector addition. U plus a negative u, just like 7 minus 7 is 0. Negative 3 plus a positive 3 is 0. Add a number to its opposite and you get 0. Add a vector to its negative or opposite and you get the 0 vector. Now, this one they don't put a name here, and maybe that's good. This is scalar C times the product of scalar D times U is going to be exactly the same as if you multiplied C times D, scalar numbers, that's just a simple multiplication, times the vector U. Now, if you had to say something here, I would call this the associative property of two scalars with a vector, okay? And that's probably why they didn't write it down, okay? They moved the parentheses, but they didn't really call it an associative property. It kind of is, but it's associative property of two scalars with one vector. Now, here is a distributive property. Scalar C plus scalar D added together times U would be the same as doing C times U plus D times U. Okay? That is a distributive property of scalar addition. Well, let's see. Scalar multiplication over scalar addition, you might say. But it works the other way too. If you had scalar C times the sum of two vectors, that's the same as C times U plus C times V. That's the distributive property of scalar multiplication over vector addition. This would be scalar addition over scalar multiplication. This is scalar multiplication over over scalar addition. Okay, both of them are distributive properties. And then this one, 1 times u is equal to u. Now, since they did it up here, I would have made this separate from this one. This one would have been the multiplicative identity property. Multiply the scalar 1 by the vector u, you get the vector u. Okay, you multiply each component of u by 1, and you get exactly the same components. Okay, so that would be the scalar identity property of the identity property of multiplicative identity of scalar multiplication, you might say. Now this one, if you multiply the scalar 0 times any vector u, you're going to get the vector, the 0 vector, every time. You can't help it, because this would be 0 times u1, comma 0 times u2. Well, 0 times u1 is 0, 0 times u2 is 0, 0, 0 is the 0 vector. Okay. I don't know if that has a special name, but that's certainly a property. Now there would be one more, and I guess they're going to show it later, but so we'll hold off and let them show it to you. Okay, let's move on. Any set of vectors with an accompanying set of vectors that satisfies the 8 properties that were listed there, I would have called them 9, listed in 11.1, is a vector space. Hey, you folks in linear algebra, you're getting a forelook at something you're going to be talking about later, vector spaces. The 8 properties, actually in his book, the same author's book, he calls them 10 properties. I won't get into the difference, they're fairly minor. The 8 properties are the vector space axioms. So this theorem states that the set of vectors in a plane with a set of real numbers forms a vector space. Okay? And here's what this one says when you get it down to it. Oh, I'm sorry. This should be on a different slide. Okay? The length of a scalar multiple. If V is a vector, and let V be a vector, let C be a scalar of any size, okay, positive, negative, fraction, decimal, rational, irrational, it doesn't matter, then the magnitude of c times v, the vector, the scalar multiple of c times v, magnitude of that would be the absolute value of c, okay, because remember, magnitudes are always positive, so whether c is positive or negative, take the absolute value of c and multiply that by the magnitude of v, which is always positive too. That gives you what your length of a scalar multiple. So if c is a little number, less between 0 and 1, or minus 1 and 1, then you're going to be a shrink. If c, absolute value of c is greater than 1, that's going to be scaling upward to a longer length. Okay. In many applications of vectors, it's useful to find a unit vector that has the same direction as the given vector. And this next theorem gives a procedure for doing this. And this is pretty important. You'll use this a lot. If v is a non-zero vector, okay, don't ever mess with a zero vector. You can't, there's a lot of things you just can't do with it. If you have it, notice, but you can't do a lot of things. If v is a non-zero vector in the plane, that means 2 dimensions, then the vector u, interesting they call it u, which is equal to, defined to be the vector v divided by the magnitude of v. Okay? Well, or you could write this as 1 over the magnitude of v times v. This vector u will always then have length 1, but it'll also be in the same direction as v. Because you're just multiplying it by a scalar, so that means you don't change its direction at all, and that amount of the scalar quantity here means you've either scaled it down or you scaled it up. If the magnitude of v was a big vector, you're scaling down because you're multiplied by 1 over a big number, that's a smaller number. If the magnitude of v was a very small number, 1 over a very small number tends to be a bigger number, so you scale it up to get to magnitude 1. Okay? Now, just as if we have a length of a vector, also called the magnitude of a vector, also called the norm of a vector, several words for that, well, so do we have several terms for this. In this theorem, 11.3, u is called the unit vector in the direction of v, and the process of multiplying v by 1 over its magnitude to get a unit vector is called the normalization of v. Now, in physics, to talk about things being normal, we usually mean perpendicular. That's one meaning. In vectors, when we're talking about normalizing, it means gets it down to a magnitude of 1. Okay? Sometimes in statistics, they'll talk about normalizing, and that also brings to the concept of oneness. Bring it down to an area of 1. Normalization. Okay? So get used to that. Doesn't mean perpendicular here, though there is a connection there, a far out connection, but there is a connection. But here it means magnitude of 1. Normalization of the vector v. Now, that's something that quite often you want to, when you're comparing things, you want to normalize them to get them to the same length. So that's what they're talking about. Generally, the length of the sum of two vectors, and this is what I was saying before, is not equal to the sum of their lengths. Okay? To see this, let's consider, this is what we looked at before. Here is vector u, it has a certain length here. Here's vector v, it has a certain length. U plus v, the sum of those two vectors, is shorter, has a smaller magnitude than the sum of these magnitudes. Just about always. And that's called the triangle inequality, mostly because of this. Because if this is, now if that was a right angle there, it'd be patently obvious, okay? Because the hypotenuse is always longer than either of the two sides. But basically, in a triangle, anytime your have one angle larger than the other two angles, and this obviously is. This is an obtuse angle here. These are the acute angles here. The side opposite the largest angle is the longest side, but it's never the same as the sum of the two sides. Even for a right triangle, it's not the same as the sum of the two sides. Its square is equal to the sum of the two squares, which is not the same. Okay, so this is called the triangle inequality. Here's how you express it mathematically. With u and v being two sides of a triangle, the length of the third side, magnitude of u plus v, is the magnitude of u plus v is always less than or equal to the magnitude of u plus the magnitude of v. The only times it's equal if they're collinear. If they are along the same line, the magnitude of u plus the magnitude of v is the magnitude of the sum. That's the only time. If there's any deviation from straight line, then this is true. Magnitude of u plus magnitude of v is greater than or equal to the magnitude of the sum. The equality occurs only when u and v have the same direction. Now, okay. That result is called the triangular inequality for vectors. Okay. Now, let's see where we are. We've gotten past we skipped example 4, didn't we? Sorry about that. Do we have time? We have 3 minutes. Let's go back and see if we can do example 4. Okay, it's a pretty simple example, I think. So let me clear the screen. Example 4. Find a unit vector in the direction of v, and here's v. Vector v is equal to, in component form, -2, 5. They seem to like that one, don't they? We want a unit vector in the direction of that and verify that it has a length of 1. So we want a unit vector in that direction. So what do? First thing we do is find the magnitude, the norm, the length, whatever you want to call that, of vector v. And that is the square root of -2 squared plus 5 squared. Remember, that is the magnitude of a vector. The square root of the sum of the squares. And that would be the square root of 4 plus 25, which would be the square root of 29. Okay, that's the magnitude. So what is the vector u? Now, when I write a normal vector, I put a housetop over it. That's an old way to express it, but that reminds me it's not just any old vector, it's a unit vector. The word u doesn't mean it's a unit vector, okay? The housetop, that means it is a unit vector. And this would be vector v minus 2, 5 over square root of 29, basically. Which means this would be the vector, which is -2 over root 29, comma, 5 over root 29. Now, they said verify. Okay, we found it. There's a u. Verify it has a length of 1. Well, how do you do that? You take the square root of -2 over root 29. That's supposed to be a minus, okay, squared, plus 5 over root 29 squared. Okay, what does that give you? square root of -2 squared would be 4. Root 29 squared would be 29, plus 5 squared is 25 over root 29 squared is 29, and that would be the square root of 29 over 29, which is 1. That's a unit vector, magnitude of 1. They said to verify it. There we have it. Okay, we've just gone over by a minute, but guess what? There will be no extra charge. We will start next time. We did the triangle inequality. We'll start next time with standard unit vectors on page 757. Okay, homework exercises here would include, oh, we just got one page away. Okay, number 3, you can find the answer at calcchat.com. Either 5 or 7, they're both at CalcChat. 5's at CalcView. Any of the odds, 9 through 15, they're all at CalcChat. 11's at CalcView. 17 is at CalcChat. Any of the odds 19 to 23 are at CalcChat. 21's at CalcView. 25's at CalcChat. 27's at CalcChat and CalcView. Any of the odds 29 through 33, they're all at CalcChat. Either 35 or 37, they're both at CalcChat. 35's at CalcView. And either 39 or 41, they're both at CalcChat. 43 should be at CalcChat. I think you can do any of the odds 45 to 47, either of those, they should be at CalcChat. I believe, I'm not sure on that one. I'm not quite sure why they're getting into this yet, but they haven't done an example in the book, but I think you can probably do it. Where did I leave off? 49 or 51 should both be at CalcChat. 49's at CalcView. 53 or 55 both at CalcChat. 57 and 59 should both be at CalcChat. Try to do 61 through 65. They should be at CalcChat. Stop there. No, I think you can do 67 through 71. They should be at CalcChat. Let me see if I'm right there. Yeah. Think you could do 73. It should be at CalcChat. 75 should be at CalcChat. I don't know. Maybe stop there. Stop somewhere in there. We'll pick up the rest of these. This is a long section. So we'll pick up the rest of those. That will keep you busy for a while. Plus you got 2 tests to work on. So sounds like you got a good weekend ahead, don't you? It should be raining most of the weekend. Get some calculus done. Why not? Any questions, issues, thoughts, concerns, problems? Anything? All right. Well, let's stop sharing. And I'm going, unless there's some question or something, I'll end the meeting for everybody. Any? I see none. So take care. Have a good, safe weekend. Bye-bye. See some of you in just a few minutes and some of you tomorrow. Bye-bye.